So I'm going to talk about the observatories first and just kind of give you context, and then Adam's going to talk some instrumentation, and then we'll talk the process of field campaign proposing for utilization. So the SGP is really the heart of all our atmospheric observatories. It's located in Oklahoma, North Oklahoma and South Central Kansas, actually, with our central and extended facilities. It's a relatively homogeneous land type environment, but we have our supplemental sites providing representation of other land types. This observatory is really focused around land atmosphere interaction and aerosols. It's been operating since 1992. There's about 88 instruments going every day. We have two radiosondes per day. We used to have 4, but this is actually due to the helium shortage. And we have an active effort to hopefully convert to hydrogen as soon as we can. That's the slowness in that effort is really to do with all of the permitting and safety requirements, getting that through DOE and whatnot. So one of the things I want to point out in the upper right, if you could think of like a Google Maps view of SGP, you might start at the top and you would see our office building at the top and drive down the road to our aerosol vans and then see our radars as you come around towards the east, and then our guest instrument facility and our main instrument field. Looking at all these tags, there's all these little pieces in there. So there's 88 instruments, there's lots of pieces in here. There's a repair facility, a calibration facility, and then there's all of the networking power and roads and everything else that goes into that. So just thinking from the observatory side and what it takes to stand these up, keep them operating, there's a lot of people that are concerned with all these other details down under the hood. So our North Slope of Alaska site, this gives us a comprehensive Arctic atmospheric measurement capability. It's been operating since 1997. There's 2 to 3 staff on this site to where there's 15 to 18 at SGP. Sandia also has 5 staff that regularly go up and work there. There's 2 UIC science collaborators, and then the University of Alaska Fairbanks also helps us with instrumentation and operations as well. So we have a main site at Utqiagvik. This is our high latitude coastal site. We have an E12 site that is a high latitude inland site that we're looking at a lot of solid precipitation and how that is measured. Utqiagvik and both of these sites near Utqiagvik they're not connected by any road. So you can see the picture in the middle. To get things there, we have to take the annual barge, which is truly annual, once a year. So we have to be prepared early. Everything has to be ready when they're ready to load that, and then it goes. Other than that, we fly things in and out. So you can imagine the complexity of planning and timing and getting things ready and actually to the site, and or cleaning up and removing things and remediating them from the site. In the bottom, you see a schematic of the North Slope of Alaska, and you can imagine, just like that picture of SGP, here you've got the schematic of the basic locations, and you're going to add instruments on top of that. You're worried about the networking, the power, the pylons that are holding these up, if they're shifting in the tundra, what's going on with all of this. We also do have some really interesting visitors. You can see the polar bear here. We also get Arctic foxes who love to chew cables, and we have a lot of ice that affects the fiber comms to the North Slope of Alaska as well. We're looking at processes here for mixed phase cloud properties, radiation albedo changes, aerosol cloud interactions, and coast to inland gradients, and then all of the other things that scientists can think of supporting and needing observations for. The Eastern North Atlantic site is our long-term observatory in an area to focus on marine cloud environment. Like its name, it's in the northeastern Atlantic Ocean on Graciosa Island in the Azores Archipelago. And this is a Portuguese territory. So for here, you can imagine everything has to go through customs. Again, there's no road. It has to get on a ship or plane. And so getting things here, supporting the instrumentation, there's a lot of timing challenges, getting people, parts in the right places at the right time. Here, we're supporting boundary layer structure, drizzle science, aerosol cloud interactions. There's an opportunity to observe a wide variety of marine cloud types. We've had aircraft field campaigns here as well. And just next week, we're actually working on getting our X-band radar back operational and doing a push for observations there. So our ARM mobile facilities, we've started these in operating in 2005. This was built on some previous smaller campaigns, one called Shiva that was out in the Arctic. And we've learned a lot from the previous campaigns, other collaborators and contributors campaigns. We all talk across the board and how we're designing and how we're working these. These are full observatories. So they operate the same type of instrumentation that we operate at our other observatories. Sometimes they will have a marine aspect to them, meaning they're hardened, or they have a more or a different type of sensitivity depending on how clean the environment is. But overall, it really is an observatory that you're moving. So we implemented the AMF1 in 2005, the AMF2 in 2010, and that brought an ability to go on ocean-going vessels. And then AMF3 in 2013, which brought an ability to have sustained measurements for 5+ years, but not a fixed site term. All of these observatories now, as we have maintained them, upgraded them, they all have a flexible configuration. So this could be something like Stormvex, where we have part of it in a valley and parts of it on different peaks on a mountain, to everything being on a pier that you see here in La Jolla for the Scripps Pier, or on the Polar Stern on one vessel. We operate safely in really, really challenging environments. These could be on ships, islands, the Arctic, Antarctica, but we're doing that to get the observations from these undersampled locations. And we do that through the identification through workshops and proposal-driven award processes that ensure that these AMFs are being deployed in alignment with what the scientific community needs are. The AMF3 is located in Bankhead National Forest now. This will be sustained over 5 years, as I was noting. This location was noted in the AMF workshop, the last AMF workshop that we had, that there was a critically important area for land aerosol cloud interactions that had not really been covered. So the awarded proposal noted the siting criteria needed to be away from the coastal influence, away from mountainous orographic influences, and it needed to be deep in a forested environment with a range of biogenic and anthropogenic aerosol influences. So believe it or not, that was really, really hard to find. And if you want to hear details of that, we can talk your ears off. But we found Bankhead National Forest, and that there was a Black Warrior Work Center that the Forest Service operated right in the middle of it. So the picture you see on the right, the opening nearest to the road in the middle, that is the Black Warrior Work Center that was the Forest Service site. And the other clearing is what we've cleared for our main instrument site. We only cleared as much as we had to in order to operate our instrumentation with a reasonable siting criteria so that the quality of those measurements would be good. In addition to that, about 1.2 kilometers away on the other side of the road is a 43-meter tower. There's 7 levels. You can see a picture of it. And thank you to Mark for that picture. It's beautiful in the middle there. And that when we removed as minimal amount of the forest as possible to stand up this tower and operate it safely. Everything has been operating since October, with the addition of the tower that has come along later. We have a main site. We have a tower site with some smaller towers in the forest. We have a C-band radar site and a KAX SACR radar site, which are cloud radar. And we have 3 supplemental locations. So the science drivers for this was really the convective clouds, the deep convection, and the process controlling aerosol optical properties, chemical composition, and size distribution, and the biosphere-atmosphere coupling being the turbulent exchange of vegetation aerosol feedback. And as you can see in the picture, the Arctic shark is in the upper left of that picture. And you can kind of see the haze, and a lot of that's what we're measuring. So that's why it's not such much of a clearer picture there. Our mobile facilities have been pretty much everywhere. We've been to all 7 continents, a lot of different environments. And the map on the left, it does look, because of how we mark these on the map, it looks like we've covered so much and we've been everywhere. And yes, we have, but these are singular observatories. So they're singular points. And so when you think about gap filling and what science needs, there is a ton of areas that the observations would still be gold, and that still need observatories that can go to really challenging areas and operate safely and get those the observations for everyone to use. In addition to those observatories, we have an integrated aerial approach. So as you can see that in the image here, you've got piloted aircraft that can go high. And even though we say it can fly low and slow, it's still higher than a lot of our other capabilities can go. We have our Arctic Shark, which can go up to 5.5 kilometers. And then our tethered balloon system. And then there's an array of universities operating small UAS and other things. And so we're using this in context of the larger capability to offer what everybody can't have for themselves, so we can bring the observations to the scientific community. We have a Bombardier Challenger 850 regional jet you see in the upper right. That one is in modification at this time. We are actively operating our Arctic Shark uncrewed aerial system. It's a 22-foot wide wingspan. It's capable of 5.5 kilometers in height. And we operate this on an annual proposal-based deployment. So we offer 2 payload options, and the annual proposal allows the PI and COIs to design the flight patterns based on whatever their scientific mission is. We have over 90 instruments that can operate in the Arctic Shark and the Challenger. Those are targeting everything from thermodynamics, clouds, aerosols, precursors, trace gases, radiation, and surface properties. And we are operating these in conjunction with our ground facility or mobile facility, and also our tethered balloon system. So we have multiple tethered balloon systems that have been operating since 2015. They can hold up to 36 kilograms. And in uncontrolled airspace, they can operate up to 1.5 kilometers. We can operate in restricted airspace higher. It takes about 2 to 4 crew members to operate this safely. These are flexible mobile platforms that we can move around. We can operate one at a time. We can operate 2 of these, or we can operate them with the Arctic Shark. We just have to handle the deconfliction plans and have the right science drivers and setup to do that. In certain areas, we can operate them in cloud. We can operate them at night. All of this depends on the location and airspace that we're in. So please, if you have questions about that, ask us. We'll help you figure that out, what the possibilities are, well before you go down a path of something that we can't maybe do. How we operate the tethered balloon system is we have a set of arm baseline measurements that we will operate those instruments to get the measurements. And then we can support things like our arm EMSL FICUS call. And that brings guest instrumentation in addition to arm instrumentation. And then additional payload availability, we could operate additional guest instrumentation that may not be associated with the FICUS call every year. With this, we can fly sustained flights and loiter, or we can do profiles and move the balloon up and down throughout the observatory time period. How we maximize this capability is we time the calls so we get all of the proposals at once, and then we can cross-reference those and make a matrix so that every tethered balloon flight is supporting multiple campaigns. And that really maximizes the use of the tethered balloon system, in addition to allowing additional guest instruments. Even beyond that, we're really trying to maximize its capability, and it's doing very well. One of the things, just kind of give you an idea of observatory operations, but just thinking about what goes on across ARM all the time. So we have these 6 observatories, plus our aircraft and unmanned aerial system and tethered balloon system. It takes about 18 months to stand up a new sighting location. So that could be done for a mobile facility or the TBS. But if you look at the upper right here, you can see while we're operating a mobile facility, we're also planning for its next location. So we're identifying and securing those suitable site locations, establishing the partnerships. We're planning and designing the layouts, making sure that we don't have any shading issues or things that will cause data quality or just bad data. We're getting permits. We're arranging the site operations staff and who's going to work it. And then we're relocating and installing that observatory. We're doing all of these things while we're meeting the laboratory's robust health and safety and environmental policies and practices. And we're doing that not only at the managing laboratory, but also across the ARM facility, which is 9 laboratories, multiple universities, probably 17 institutions, plus all of our users and any guests that are coming on. So this is a highly coordinated activity, and it requires a lot of ARM processes, coordination, collaboration across a lot of people. And then we have things that ARM assets are not just one laboratories. ARM assets are across the entire user facility. So we think of everything within ARM as arms, and we have to be responsible for that. So there's a lot of effort that goes to property tracking, moving the property, installation of the property, changing that, and auditing of all of that property. And that is going year round, all the way across the user facility. All of our instrumentation that Adam's going to talk about, we have to have it calibrated. It has to get repaired when something goes wrong. We have to monitor it to find out what's going on and when it's going wrong so that we can do something about it. We have data processing and archiving so that we can disseminate this information to the users, which is our ultimate goal. And so each of these instruments, the platforms, the observatories, all of these things have their own timeline. So you can imagine just the layers of program and project management and coordination that goes on. So you'll see us, look a little bit disheveled and bags under our eyes, and you'll kind of understand why we're getting that way. But we honestly have a very service-oriented staff across ARM, and we all really love doing it.